In this lecture, we're going to review some concepts of vibrational spectroscopy and potential energy surfaces, and then describe harmonic oscillator versus the Morse potential and how that alters the vibrational structure in a molecule. So a bit of review off the top here. We can talk about what we've learned from quantum mechanics in terms of the energies allowed in a molecular vibration. Remember now, atoms don't have vibrations or rotations, only molecules do. And so the energies that we've derived for molecular vibrations look like this: h bar square root of this spring constant or bond constant over the reduced mass. And then you have this quantum n plus 1/2, right? Where n can be any integer, 0, 1, 2, 3, positive integers all the way up. Okay, this is also equal to, written another way, h nu times n plus 1/2. Okay, so the nu here is our 1 over 2 pi square root of k over mu. Right, so again here, k is our spring constant, or sort of the bond force constant. Mu is the reduced mass. H is Planck's constant, and n can be 0, 1, 2, 3, etc. And where do these numbers come from, right? Where do these energies come from? Well, in previous lectures, we've solved an equation for this, and that equation, of course, is, as it always is in quantum mechanics, the Schrödinger equation. So these energies, as a function of n, the different eigenenergies based on the different allowed eigenfunctions, pop out of this Schrödinger's equation. Now, of course, this is a more complicated question than it looks, because this Hamiltonian here is accounting for the different energies. There can be a kinetic energy operator, and there will be, and there can be a potential energy operator, which there will be. And so in solving Schrödinger equation for our vibrations, we used this operator as our potential, V. And we were considering sort of a one-dimensional potential, V of x, and we used a harmonic potential, 1/2 kx squared. Okay, to connect this to classical ideas, we used the harmonic oscillator, which is what we use to predict pendulum motion, any periodic motion, and a molecular vibration should be like that periodic motion. And so that's what we plugged in for our potential energy operator, and appropriately had some kinetic energy operator terms. We came up with the wave functions that satisfied the Schrödinger equation using this harmonic potential. And these are the energies we got out. Okay, the eigenfunctions, of course, here, we're going to talk a lot about these today and in the next lecture. Right, the eigenfunctions here were made up of some normalization constants, some what we'll call Hermite polynomials, h, and some Gaussian functions, g. Okay, so we'll write out exactly what each of these terms are later on, but just for review, these were the wave functions that satisfied the Schrödinger equation, and these were the energies that came out. So this frequency here is a lot of times how you'll see it referred to in terms of vibrational energy. That's the vibrational frequency, a frequency in terms of the period of the motion. So the harmonic potential gives us these energies and these eigenfunctions. Now, a harmonic potential looks like exactly what it sounds like, something that's harmonic and symmetrical. Okay, so here's our harmonic potential. It looks exactly like x squared, right? So that's our harmonic potential, V of x. Now, an actual potential energy surface, as we've seen and we'll talk more about shortly, looks more like this. And the right side kind of asymptotes here. It doesn't go up forever like the harmonic oscillator did. And so this is a potential energy curve where the y-axis here is energy and the x-axis here is a bond distance or bond length. And these are our familiar potential energy curves or potential energy surfaces. Previous lectures, we talked about Jablonski diagrams, right, of having these static energy states with vibrational levels on top of them. Well, that's a simplified picture of this. And so there should be exactly this vibrational ladder going up here. And these are the additional vibrational energies where n equals 0, n equals 1, n equals 2. Okay, now some quick review. If we're talking about a diatomic, which is what we're going to talk about today, something like O2 or N2, when we first think about these types of potential energy surfaces and vibrations, how many vibrations are in a diatomic? From statistical thermodynamics, we know vibrations in terms of numbers go by the rule 3n minus 6. It's a degrees of freedom argument. There's 3 times the number of atoms, so n is number of atoms here. And this is the formula we come up with for degrees of freedom left after considering translations and rotations. 3 translations, 3 rotations. There's 3n degrees of freedom total, so what's left for vibrations? 3n minus 6 from rotation, 6 from translation. Now, if it's a diatomic, it's 3n minus 5. Because of the symmetry down the bond, there's one of the rotations that is not a real change in anything. You're just rotating around a symmetrical axis. And so this is the rule for diatomics. Great. So, how many vibrations are there for a diatomic? Well, for a diatomic, n equals 2. And so there should be 3 times 2 minus 5, 1 vibration. So why are there different levels here? Why is there a ladder structure for all these? If this is the surface of a diatomic, like nitrogen or oxygen molecules, or hydrogen or chlorine, or HCl, why are there these different vibrational energy levels? Okay, here's the difference. There is one characteristic vibration with a characteristic vibrational energy, but for that singular vibrational frequency and type of vibration, there's actually different quantized motions of that vibration. Okay, so in a diatomic, there's only one vibration. What is it? Well, it's these 2 atoms moving apart and then moving back together, vibrating along this coordinate. And it has a certain frequency nu. Okay, so for that one vibrational frequency, there actually is a lot of different vibrations, but it's a different vibrational amplitude of that frequency, right? Frequency here is how many times the atoms are moving back and forth per second, but the amplitude is what's changing here. So there's a ladder structure for each of these different vibrational frequencies. In a diatomic like we're showing here, there's only one vibrational frequency, but there still are different amplitudes of that vibration. So let's think about this in the n equals 0, the lowest possible state of vibration. It has this certain frequency, whatever it is for this particular molecule. And what this ladder here, this rung of the ladder here symbolizes, and the length of this bar, tells us how far apart, to the right, the atoms get, and how close together the atoms get, right? Because this x-axis is the bond length. Xe here is the equilibrium bond length. So maybe for nitrogen or whatever, this is the equilibrium bond length here. But when it's vibrating at this certain characteristic vibrational frequency, how far apart are the atoms actually moving? Okay? And this shows you they're getting this far apart. So maybe over here at the longest part of this first ladder, well, now the molecule is this far apart. And of course, this should be drawn much more straight here. So that would be the largest amplitude. And maybe on the left here, we'll maybe call this x short and x long, right? Where x is the bond length that we're caring about. You could call that r. I'm just calling it x here, right? This is xl. And maybe xs is they've moved closer together. Okay, so this is the picture of molecular motion you want to have in mind for a vibration. There's a characteristic moving out, right? And then moving back in for vibrational motion. The frequency of that is a certain number of times per second, but how far out does it go? Well, the length of this shows you on the x-axis how far out the atoms move, and it shows you how far in the atoms move as well. So, the different energies here in the eigenenergy formula that we got from harmonic oscillator solving the Schrödinger equation are for different rungs of this ladder, different quantum states that represent different amplitudes, not different vibrational frequencies. Okay, so the different vibrational states here all have the same frequency, whatever nu is. Now, if it's a diatomic, there is only one vibrational frequency. If it's a polyatomic, there are a bunch of different vibrations, each of which will have their own ladder rungs with different amplitudes associated with that vibrational frequency. Okay, since this is a diatomic, there is only one vibration, but that vibration is able to be amplified if we add energy to it. Okay, so the different vibrational states, here all have the same frequency, but have different amplitudes. And so that's what's happening when you're adding energy, shining light on a molecule. And we've talked before that the separation here in between levels happens to correspond to IR light. So when you're doing IR spectroscopy or you're shining IR light at something, you are sort of amplifying the nuclear motion while maintaining it at this certain vibrational frequency. So they have the same frequency, but have different amplitudes. Okay, so if you're going to add some IR light and cause this vibrational ground state to be excited to this n equals 3 state up here, well, what are you doing? You're not changing the frequency of that vibration. What you're changing here is how far out the atoms get in that certain frequency and how far in they get. That's what you're adding in IR spectroscopy. Okay, so that's the picture we want to have in our mind. We can transition between these different amplitudes by absorbing or emitting light, but the frequency of that motion doesn't change. And so this is hard to draw, right? But imagine these things rattling back and forth, the atoms moving back and forth at a certain frequency, right? But as I pump, so I'll draw it in a reduced coordinate here if it's only, a center of mass or something we're thinking about. Imagine it's one thing that's moving back and forth with a certain frequency. It's still, as we add energy to the system, going to take about the same amount of time to get back to the same place, right? But it's going to be going further out and further in. So that's the same frequency of motion as this, but it's getting further out and further in. So that's what we're doing here when we're adding IR light to a molecule. In this case, it's a diatomic. There's only one frequency of vibration, but that's what we're doing. Now, the bars I've drawn here and the energy formula that we've been talking about was based on this, which is a formula for harmonic motion, harmonic oscillator, right? Meaning the amount you go in will be the same as the amount you go out, okay? 1/2 kx squared. Now, Does the potential energy of a molecule really look like that? No, right? The potential energy here does not look like this. It sort of does maybe up to here, but then it turns over, right? And goes out. So this harmonic oscillator, the eigenenergies that come out, the eigenfunctions that come out, are a decent approximation for lower temperatures of only these states, but as I go up in energy and get to the higher states, I'm going to see something a little different, okay? And it's going to be different because the shape of the potential that goes into the Schrödinger equation, in terms of the Hamiltonian, which is made up of this, is going to be different because the functional form of the potential is different, okay? So what you really would want to do to get an accurate set of eigenenergies and predict what kind of light might be absorbed by your system is to solve the Schrödinger equation with what's called an anharmonic potential. Okay, so an anharmonic potential is one that isn't symmetric, not harmonic. And this is how molecules actually operate. Why? Because if we think of a simple picture here, right, of the atoms, and I'm going to take this atom and move the second one further out, is there going to be a great difference in energy between this, where they're already really far apart, and this? No. Okay, so on some energy diagram, if I go from this distance to this distance, there probably shouldn't be a big change along the y in energy because these atoms are already probably too far apart to actually bond with each other. Okay, so the energy shouldn't go up from here to here. It should probably flatten out, and that's what we see with our anharmonic potential. Now, as the two atoms approach one another and this starts moving towards my first atom, well, at some distance, right, the electrons around atom B, we'll call it, start seeing the nucleus of atom A. That's favorable, and the energy goes down. And there ends up being some minimum in energy. This will then be the equilibrium bond distance, and this then is my ground state energy for this particular organization of electrons, right? This whole thing is dependent on, well, and this is what we talked about last time, what is the organization of orbitals here? And what is the term symbol to go along with that? Okay, so the energy skyrockets on the left of this potential because eventually you put atom A, sort of the nucleus, on top of atom B, and that's unfavorable. Okay, so that explains the left side of this. The right side of the potential is explained by the fact that at some distance, it doesn't matter if I move the atoms a little bit further apart, because the atoms are already far away from each other that they don't really notice one another. Okay, this anharmonic potential, the exact functional form here, was actually first identified. The anharmonic potential for molecules was first identified by a brilliant scientist by the name of Philip Morse. And Philip Morse was an American physicist. He actually worked at Princeton and MIT. But he's the one that took this and said, yes, 1/2 kx squared is fine and good, but that doesn't make physical sense in terms of molecules. So I'm going to make a potential that is more accurate to how molecules should behave. And so my potential is not going to be 1/2 kx squared. It's going to look like the following. D sub E, we'll define in a second, times 1 minus e to the negative alpha x minus xe quantity squared. Actually, it's all of this quantity squared. Okay, so let's talk about some of these terms. dE here is the dissociation energy. Alpha here is lumping some terms together, but it's going to be that spring constant we're familiar with. over 2 times this dissociation energy. Okay? Again, xe is this equilibrium bond distance, and x then tells us essentially this quantity is how far away from the equilibrium distance are you. If you're exactly at it, then of course this goes to 0, right? But x is where you are on this harmonic oscillator, or sorry, anharmonic oscillator, and xe is about this fixed equilibrium position. So this is a constant, this x of e, for a particular type of molecule. So for nitrogen, this is just a number that you're plugging in here, in the same way that you're just plugging in a number for the constant for, say, nitrogen, and the dissociation energy for nitrogen. Okay, so now this is the functional form. This dissociation energy we can actually draw, and maybe we'll draw this a little bit bigger over here. Here's the energy. Right, this still is my bond length, or bond distance, or radius between the two atoms, and the potential starts up here. It looks very harmonic in nature, and then it sort of turns over and flattens out at some point. Okay, now the bottom of this, again, I could probably do a slightly better job of this. The bottom of this is my equilibrium bond length, and so this would be the lowest energy here. And the dissociation energy then is this height, right? From the bottom of here to the asymptote of this curve, that is this dissociation energy. And so if you put this formula, right, into your Hamiltonian, along with the kinetic part, and resolve the Schrodinger's equation, you get the following. So solving Schrodinger equation with the Morse potential here, this anharmonic potential, the eigenenergies we get look like this. A part that's the same as the harmonic oscillator, minus this next part, which we're going to call an anharmonic correction. Okay, so we get the same, eigenenergies out here as we do from the harmonic oscillator, solving that. But now we get these extra energies because, well, we've changed the potential. Okay, so this is h nu, the frequency of this vibration. If a diatomic, it's just a single vibration, but there's different quantum states here, n equals 0, n equals 1, etc. This is minus h nu quantity squared over 4 times the dissociation energy, whatever this difference is from the asymptote down to the bottom of the curve. Quantity here times n plus 1/2 quantity squared. So in the harmonic oscillator case, the eigenenergies that we're counting up from n equals 0, right, to n equals 1, to n equals 2, to n equals 3, to n equals 4. Well, the difference in any of these, okay, is just h nu, right? The energy of this one down here is 1/2 h nu. The energy of this one is 3/2 h nu, 5/2 h nu, 7/2 h nu, 9/2 h nu. So these differences are all h nu, okay? And so the harmonic oscillator with its harmonic potential that looks like this has a symmetry to its eigenenergies. They're all equally spaced. But in the anharmonic potential and real molecules, this isn't the case, okay? Because the harmonic potential, you could see IR light that excites from, oh dear, I'm gonna have to fix that. Good enough. So the harmonic potential, right, that is exciting from the ground state to the first excited state will be the same type of light as we're using to excite from the first to second state, right? Or the second to third state, or the third to fourth state. So the difference in any of these are the same h nu, so it would take the same kind of light to excite between those. And so in the harmonic oscillator case, if molecules behave that way, you couldn't actually have strictly vibrational spectroscopy because you wouldn't really be able to tell between a promotion that was V0 to V1, right? Or, well, maybe I should call these N since that's what I've been calling them. N0 to N1 vibrational transition would be the same as N1 to N2, would be the same as N2 to N3. So you wouldn't have this, fingerprint of the different vibrational states because they're all spaced the same way. But luckily for us, vibrational states are not spaced evenly because the potential is not harmonic. Okay, and so the potential here is the Morse potential, and so we don't get evenly spaced states. And you can convince yourself of this, and probably should, by plugging in n equals 0, n equals 1, n equals 1 to n equals 2, and solving for the spacing. This square term here means it's not going to be equal between successive states. And so the way that a Morse potential eigenenergies look is here is n equals 0, here is n equals 1, n equals 2 is a little more closely spaced, n equals 3 is a little more closely spaced than the previous two were, and n equals 4 is a little more closely spaced than 2 to 3 was, and n equals 5 is a little closer spaced than 3 to 4 was, and so on and so forth. Okay, so as I go up in energy here, and I'm deviating more from the harmonic potential, I start to see more deviations, a stark contrast, in the energy spacing. And eventually, these energy states really get, crammed close together. All right, they're very, very densely packed at some point. Now, in the harmonic case, there's an infinite number of stable energy levels, right? But here you can imagine if I go above this energy, well, that's when I'm changing the bond dissociation energy and I'm breaking the bond. Okay, so at some point here, I'm actually going to break this bond, and it could be a question to you, how many levels or ends here fit before I break the bond, right? How vibrationally excited can I be before the atoms just fall apart and I break the bond? Okay, so how many energy levels fit in here? Well, of course, it depends on the size of this dissociation energy, but this can be solved by thinking, well, the energy has to be less than or equal to this dissociation energy, right? These are the energies that I'm solving for the different ends. And so that energy can exceed the dissociation energy. Okay, so you can, if you want to know how many ends fit in this potential well, right, this particular Morse potential with this depth d sub e, well, the thing you do is instead of calling this energy, you just call this dissociation energy, right? Whatever it is here, 2 eV or something, who knows? 3.2 eV, who knows? 150 kilojoules per mole, whatever your favorite unit is. Make sure the units you're using here for the vibrational frequency and Planck's constant align. But whatever that number is, plug it in here, okay, and solve for the n. And you might get an n like 17.3, okay? That means n can vary from 0 to 17. And n of 18 would be greater than the dissociation energy and is not allowed, okay? And so in that case, for that particular dE, maybe this is the n you solve for, and now you know there's 17 of these vibrational levels for that given dissociation energy. Now, the last thing I want to mention here is that this dE, this dissociation energy, actually isn't the bond energy, okay? This is dissociation energy relative to the bottom of the well. But we know from quantum mechanics and Heisenberg's uncertainty, we can't be at the bottom of this well, can we? Right? If we're at the bottom of this well, then we know the energy, and we know the position of the system simultaneously. Heisenberg says, no, no, no. Okay, so you can't be there. You have to be in this first vibrational state where there's some uncertainty to what the bond distance is. Okay, so really, this dE is the difference between the asymptote and the bottom of the curve, but that's not the bond dissociation energy. Okay, that's not the bond energy is what I should say. The bond energy, how much energy is stored in the actual chemical bond, this vibrational energy offset right here, okay, is strictly about motion of nuclei. So the bond energy is actually from this asymptote to the lowest vibrational state, not to the bottom of the curve. Okay, so this is called D0, where dE is called our dissociation energy. Okay, how much energy does it take for the molecule to fly apart? And D0 is the bond energy, because that's how much energy you need to overcome just the bond, because this is the vibrational energy of the nuclei. Okay, so that's a subtle difference there between D0 and dE, right? And the bond energy here, D0, is dE, the dissociation energy, minus the energy of vibrational state 0, right? So whatever the energy of this state is, right, relative to the bottom, that's this vibrational energy E sub 0. Okay, so make sure you're not getting confused between dissociation energy and bond energy, right? Make sure we understand the physical process of what's happening if I walk to the right or the left on this curve. If I excite this vibrationally, the molecule might be vibrating like this between these two distances, and I add some energy, and now I'm up here, and I'm vibrating between this distance and this distance. And what you'll see, what's really quite interesting to me, is as you get towards the top of this potential, think about this. And with each subsequent vibrational energy you're getting to, you're moving a little bit further closer together, right? But look what happens on the right. As you go up in energy, you are really now exaggerating how far apart you're getting, right? Your distance here is much larger than your distance here. So as you go to higher and higher vibrational states, the furthest apart they're getting is getting further and further much faster than the closest they're getting is getting closer together, right? So as you pump energy into the system and go up this ladder, right, and vibrationally excite, okay, the amplitude is moving back and forth to greater degrees. The atoms are getting closer together and further apart. The frequency of that motion is not changing. It is always just new for this particular type of vibration. So the atoms are getting, as I go up and up and up, right, the atoms are getting closer and closer together. But as I go up and up and up, they're really getting further apart. They start here, they go out to here, then they jump and go all the way out to here. Right? So it's becoming exaggerated how much time and how much further apart the nuclei are getting. So that'll do it for this lecture. Next time we'll derive the selection rules and talk about how this relates to the atmospheric components that absorb IR light and how that's related to climate change. So a lot more calculus and derivations along with the application here of this vibrational picture in the next lecture. See you then.